So here we're going to find the derivative of the absolute value function. So the absolute value function, we've already talked about this, but it's defined to be a piecewise function. It's broken up into two pieces. There is a negative side where x is less than 0. We define it on negative x, okay, less than 0. And then if x is greater than or equal to 0, we define it to be positive x. That way, if I have a negative, say I do the -5 here, that's less than 0, so it falls in this camp. So that's -5 times negative, which gives me a +5. And if it were like a +4, well, I fall into this camp, and then it's automatically just write out x, okay? So that's how it strips away the negative. All right, now I want to figure out the derivative. So I need to break this thing up into cases. Since it's a piecewise, I need to consider 3 cases. Case number 1, x is less than 0. So we're dealing with values over here. So what does the slope of the tangent line look on the left side of this graph here? So if we're considering the left side of this graph, then we're considering this part of the function here, negative x. So I need to take the derivative of negative x. So I'm going to use the definition of the derivative for negative x here. And so that's the limit of, well, remember the definition of the derivative, f of x x plus h minus f of x over h, right? Taking the limit as h goes to 0. So my x plus h is negative, so I put the negative in here. And then I minus the minus x. Now when I work through that, what's going to happen? A minus becomes a plus. And so I have minus x minus h plus x. So the negative x and the positive x canceled. I'm just left with negative h on top and an h in the denominator. So limit as h goes to 0 is 0 over 0. But if the h's cancel, then I get -1. Limit as h goes to 0, -1 is simply -1. So for any x values that are less than 0, the derivative is equal to -1. That's what this says, which makes sense. The slope of this line here is a -1 slope. It's a constant slope. It's constantly -1. Therefore, whenever I plot the derivative, I'm dealing with everything x less than 0 is a -1 value. It's a constant, okay? So you're starting to see a pattern here. Derivatives of lines are constants, okay? You saw in a previous one that the derivative of a parabola is a line. So you're starting to see a little pattern coming along here. So derivative of a quadratic is a line. Derivative of a line is a constant, and so on. So you might be able to form some ideas here. So just a little foreshadowing for you. Now let's consider case 2. Okay, so case 1 was less than 0. Case 2, x is greater than 0. So I'm going to consider only x values that are greater than 0. So that puts me into this category here. So f of x is equal to x. So I'm going to use my definition of the derivative. And so that's x plus h minus x. Okay, I just plug it in, right? If f of x equals x over h. Now what happens? X and x cancel, and I have h divided by h. And I take that limit as h goes to 0, and I just get 1, okay? Now, if I'm going to plot this, that means that for any x that is greater than 1, or greater than 0, then I have a slope of 1. That makes sense here because this line has a constant slope of 1 for any x that you pick. And so over here, I have this horizontal line on the positive x-axis side, okay? Now the last case I need to consider is where x is equal to 0. Right now we don't have the derivative defined. It's defined for all values. So far we've defined it. It's the derivative is defined for -infinity to 0, and then from 0 to infinity. So we just got to check is it defined for x equal to 0? That's the last case. So let's see what's going on here, okay? Now, looking at the graph intuitively, what would we think? Well, I mean, you got a couple options here. Maybe the slope is a positive one, but heck, if it's at 0, I mean, it could be a negative one, right? Or maybe it's like a slope of 0. Who knows, right? It seems like it could just be all sorts of things when it's at a tip of a point like that. So let's use math and figure this out instead of just saying it seems like it. So since f of x is a piecewise, we switch the pieces at x equals 0. So we're switching between these two here. So what that means is I need to do left and right-handed limits. So if I do left and right-handed limit, let's do the left-handed limit first. So if I do a left-handed limit, these are x values that are less than 0. That means I'm dealing with the negative, okay? So look, we're heading to 0, okay? So my value I'm plugging in is 0 here, okay? I'm no longer using the x. I'm taking the derivative. I'm using the definition of the derivative at a point, okay? So I'm choosing x equal to 0 here. That's this case here. So instead of doing x plus h, I'm putting 0 plus h, right? My x is equal to 0 here. And so what does this become? This becomes negative h minus 0. Okay, why is it negative? Because for x less than 0, I have negative, okay? So technically this would be like negative x plus h, right? That's what we had written. But here, instead of x, I had 0 plus h, okay? So that's where that negative h is coming into play. And then minus your 0. We used to have minus x, but x here is 0, so that's minus the 0 right there. That's where that's coming into play. So when I simplify here, I have negative h over h, which simplifies to negative 1, okay? So this says, coming in from the left side, my slope is negative 1, and that makes sense. When I consider x values close but on the left, that's a negative 1 slope, okay? Makes perfect sense. Now let's consider values on the right side. Now on the right side, if I pick x values on the right side, clearly this gets me a slope of a positive 1, okay? But let's run through the math here. So I plug in 0, okay, derivative at a point. I plug in the point there. And so what does that get me? That gets me h minus h. Remember, derivative at a point. On the positive side, x greater than or equal to 0. What does that tell me? That means I just use the x function. So I plug in 0 plus h into x. I just get h, okay? Minus f of 0, so minus 0. Gets me h in the numerator and h in the denominator, simplify to 1. Okay, so what does this tell me? This tells me I have a left-hand limit of negative 1 and a right-hand limit of positive 1. Therefore, the limit as h goes to 0 of f of 0 plus h. Remember, look, guys, this is the definition of the derivative at the point f of 0, right? That's different than saying the limit as h goes to 0 of f of x plus h minus f of x over h. That's f of x, okay? You see, we replaced x with what? We replaced it with 0 here. So that's what we're doing, the derivative at a point there. Okay, so that's the definition of the derivative of a point, right? We're only considering one point, x equal to 0, okay? Just want to make sure we're on the same page here. There's a nuance of a difference, but there is a difference. Now, this is equal to f prime of 0. And what do we say? This does not exist because the right-hand limit's 1 and the left-hand limit is negative 1. Looking at this graph here, we can clearly see if we were going to try to figure out that derivative, we'd see that we had a negative 1 derivative on this side and a positive on this side. And if you plot it, you can see that there's this jump going on here for the derivative function, okay? So what does this tell me? That tells me that f is not differentiable at 0, okay? But f is differentiable for negative infinity to 0 and then union 0 to infinity. So the absolute value function is differentiable everywhere except for at that sharp turn right there. That's the only place that it's not differentiable, okay? So pretty close. Now, in general, functions are not differentiable at a point, okay? I'm stressing at a point, right? Not differentiable at a point using that definition, right? If there are any discontinuities, okay, remember it's a necessary condition to be continuous, right? So to be continuous, that's a result of being differentiable. So if it's not differentiable, it's not continuous. Okay. Now, that means if you've got a hole or a jump or an asymptote there at the function value, or at the x value of the function, then that means that it's not differentiable at that point. Okay. You could be not differentiable at the point if there's a cusp. Now, what the heck is a cusp? That's a sharp turn. So an example for the problem we just did, there exists a cusp right here at x equal to 0. It's a sharp turn, okay? So it's not differentiable at that point. And then the last example, you might not be differentiable at a vertical tangent line. So what does a vertical tangent line look like? Well, let's do a graph and you can see a picture here, okay? So I want to explain why it's not differentiable at these three options, right? So the first one I'm looking at is this one right here. I have a vertical line, a vertical asymptote here. So at x equal to -5, we have a discontinuity of type 1 because there's this vertical asymptote. Now, at x equal to -3, what do we have going on here? It looks like we have a hole in the graph. Well, looks like, you'd have a derivative right there, right? But we're saying the derivative at a point. But guess what? The function is not defined. It's not continuous at that point. Therefore, at x equal -3 fails by discontinuity again. If it's discontinuous at the point, it's not differentiable there, okay? Continuity is a direct result of being differentiable, all right? So if you take the derivative and it exists, and that means that it's continuous at that point there, okay? Now, what about x equal to 0 here, okay? So this is an example where we've got this function here and it curves up and then it kind of bends over like this. So what's happening here? There's actually this vertical tangent line going on here, okay? So when you have a scenario where you've got a vertical tangent line, an example here, I don't know if you remember the cubic function. So the cubic function kind of looks like this when you graph it. It's got that vertical tangent line going on right there. The cubic function is actually not defined for x equal to 0. Okay, so that's what the scenario that's going on here. Now, what's going on here? Why is it not continuous, or why is it not differentiable here? Because it's actually discontinuous. Another one example, okay? And then the last one right here at x equal to 4. Why is this one not differentiable? Because of the cusp. So this is a number 2 reason right here, okay? It's the sharp turn. So what are we looking for when we're talking about differentiable at a point? We're looking for a graph that is smooth and continuous, and therefore then it will be differentiable at that point, okay? So that's what we're looking for when we're trying to figure out, is this function differentiable at the point, yes or no? And so these are the three in general reasons why you might not be differentiable at a point.